We've never seen it, never touched it, and yet it seems to hold the entire universe together. This elusive substance known as dark matter constitutes the majority of what exists in the cosmos. Recently, for the first time, a highly advanced artificial intelligence system detected something within dark matter behaving unlike any known form of matter. It pulses, flows, and reacts. According to physicist Michio Kaku, it might even be alive. If that's the case, our understanding of the universe could be on the verge of a fundamental shift. This isn't about extraterrestrial beings. This is about a potential new form of life concealed within the unseen regions of space. The implication is profound. We may not merely be observing the universe anymore. It might, in fact, be observing us. Consider what it means to live in a reality where most of the environment around you is invisible, not because of a visual limitation, but because the universe itself is built that way. All the matter we know, planets, stars, galaxies, even our own bodies, accounts for just about 4% of the total mass and energy in existence. The remaining portion, completely hidden from view, is referred to by scientists as dark matter. Unlike the atoms that make up visible matter, dark matter neither emits nor reflects light. It's entirely undetectable through direct observation, yet it possesses mass and exerts gravitational force. That gravity shapes the very architecture of the cosmos. One may reasonably ask, if it's invisible and intangible, how do we even know it exists? The key lies in how galaxies move. When researchers study the rotation of galaxies, vast collections of stars, they find something puzzling. Stars near the outer edges move much faster than expected. Based on our understanding of gravity, these stars should have been flung out into space, but they remain in orbit. Something unseen must be anchoring them, something that can only be explained by dark matter. Michio Kaku once described dark matter as the most enigmatic material in the universe. It doesn't radiate or reflect light, yet it holds galaxies together like invisible glue. This binding force enables galaxy clusters to exist at all. Dark matter isn't a peripheral component of the cosmos. It forms the fundamental framework upon which the entire universe operates. Despite its invisibility, dark matter leaves measurable imprints everywhere. It shapes galaxies, influences star movement, and leaves traces in the cosmic microwave background, the faint residual radiation from the Big Bang. Current estimates suggest dark matter is about 5 times more abundant than ordinary matter. That means for every spoonful of visible atoms, there's a handful of something else lurking just beyond our sensory reach. With sophisticated techniques like gravitational lensing and now artificial intelligence, we are starting to glimpse how dark matter behaves and, potentially, how it thinks. To truly grasp how strange and fascinating this concept is, we must go back to when astronomers first noticed discrepancies in the cosmos. In the early 20th century, Dutch astronomer Jan Oort studied stellar movement within the Milky Way. At that time, the idea of galaxies beyond our own had only just gained acceptance. Oort set out to analyze the motion of stars in our galaxy and found that those on the outskirts were moving too quickly to be held by the gravitational pull of the visible matter alone. Around the same time, another scientist, Fritz Zwicky, examined the Coma Cluster, a massive congregation of over 1,000 galaxies, and noticed a similar anomaly. The galaxies behaved like bumper cars, colliding and speeding through space, yet the entire cluster remained intact. Zwicky concluded there must be an unseen form of mass holding it all together, which he named Dunkelmaterie dark matter. His calculations indicated that this invisible material was hundreds of times more abundant than what could be observed. At the time, his ideas were dismissed as too radical, but he stood by them, insisting that no other explanation fit the data. These early findings were the first major hints that our understanding of the universe was incomplete. Even though neither Zwicky nor Oort could identify what dark matter was composed of, They both recognized its influence on the largest cosmic scales. Their groundbreaking observations opened the door for decades of further research and led us toward even deeper mysteries. One of the most significant advancements came in the 1970s. Thanks to American astronomer Vera Rubin, she wasn't trying to overturn existing theories. She simply wanted to understand how galaxies rotate. Using cutting-edge instruments of the time, she started by examining the Andromeda Galaxy. Based on Newtonian physics, she expected to see stars at the galaxy's edges moving more slowly, similar to how planets in the outer solar system orbit more slowly than those near the Sun. Instead, the stars were moving just as fast as those closer to the galactic core. The only explanation was that something unseen and massive was contributing additional gravity. This revelation brought the concept of dark matter back into scientific focus. What Zwicky and Oort had hinted at decades earlier, Rubin confirmed with solid, repeatable data. She discovered the same rotational behavior in numerous other galaxies. As she famously said, "We don't see dark matter. We see its fingerprints all over the place." Her work demonstrated that galaxies are surrounded by vast halos of invisible material. Without this, the structure of the universe simply wouldn't make sense. Despite the monumental impact of her discoveries, Rubin was never awarded a Nobel Prize, an omission many consider a serious oversight. Nevertheless, her contributions were honored with the creation of the Vera Rubin Observatory, a facility dedicated to studying the hidden components of the cosmos. Her work made it clear, dark matter isn't hypothetical. It's a real dominant part of the universe. But observing it isn't the same as understanding it. To probe even deeper, scientists needed an entirely new tool, one capable of peering not just through space, but through time itself. That tool turned out to be gravity. Gravitational lensing operates like a natural cosmic magnifying glass. Imagine looking at a bug through a curved lens, not made of glass but of gravity. When light from a distant object, like a faraway galaxy, passes near a massive foreground object, such as another galaxy or cluster, it bends. This effect, predicted by Einstein's theory of general relativity, was first confirmed by Arthur Eddington in 1919 during a solar eclipse. Since then, gravitational lensing has become one of the most powerful tools for detecting dark matter. When the alignment is just right, this gravitational distortion creates arcs, rings, and even formations that look like celestial smiley faces. More importantly, these distortions allow astronomers to infer the presence of invisible mass. If the bending of light is stronger than expected based on visible objects alone, then dark matter must be contributing additional gravity. This effect allows scientists to map the otherwise undetectable. As theoretical physicist Priyamvada Natarajan put it, gravitational lensing offers the most direct evidence we currently have for dark matter. It's like tracking an invisible figure by the way the crowd moves around it. One of the most telling examples is the Bullet Cluster, a collision between two galaxy clusters. The stars passed through each other mostly unaffected, while the gas slowed down from the impact. Remarkably, the dark matter appeared to continue unimpeded. Gravitational lensing showed that the gravitational pull, i.e., the mass, remained with the dark matter. This provided one of the most convincing arguments yet that dark matter is real and not simply a gap in our understanding of physics. But recently, something even more surprising emerged. When gravitational lensing data was processed by a sophisticated artificial intelligence system, the results were startling. The AI didn't just reveal static structures. It uncovered motion, patterns, and rhythms within the dark matter fields. These patterns weren't random. They followed cycles and loops, resembling biological systems. The dark matter wasn't behaving like lifeless material. It showed signs of dynamic organization. What the AI detected bore an uncanny resemblance to processes seen in living organisms: heartbeats, neural rhythms, and metabolic cycles. It was as if dark matter wasn't just a passive substance. It was responsive, adaptive, and possibly communicative. Michio Kaku remarked that, if this is true, we may need to redefine what it means to be alive. This suggests dark matter might not just be the stage for cosmic activity, it could be an active participant, a system that processes information or exhibits lifelike qualities. Naturally, the scientific community responded with both excitement and caution. Patterns can sometimes appear in random data, and AI systems are not immune to misinterpretation. But what set this discovery apart was its consistency. The eye identified the same rhythms across unrelated datasets. Even simulations built from different observational sources revealed similar feedback loops. The odds of this being pure coincidence are low. If confirmed, we may need to accept that dark matter forms not just a structure, but a system. And if that system behaves like something living, could it also possess consciousness? Some experts notice that the patterns in dark matter distribution resemble the architecture of the human brain. Billions of neurons in our brain are connected through synapses, tiny junctions that transmit signals and store memory. Scientists observing dark matter's behavior saw similar designs, vast, interconnected webs spanning galaxies.